All right, let's talk about moments. And you remember that force is a push or a pull. And if you're at your house or apartment and you put a book on the table like this, and you push on the book, push right in the middle, you'll push it across the table. It'll slide along with your line of action. If you move your hand off center so you're pushing on one corner, now it won't slide, it will turn, it will rotate. And when you push or pull, you can move a body one of two ways. And the fancy way of saying it, sliding across the table, is translation. That means it moved from one spot to another. Another way it can move is rotation, and this is what is involved when we have moment. And the only way a thing can rotate is if you go out some distance away from the pivot point and push out there. An example is a revolving door in a building. So if I test this door, I try to go through this door. If I do like this top image here, if I walk into the post in the middle of the door and try and push on it, the only thing that will happen is I will mash my nose. If I want the door to turn, I have to move out to the end of the door and push, and now it rotates. And this takes us to the idea of moment. Moment is the tendency of a force to cause rotation. And you can figure out moment with this formula. Moment is force times distance. Like with this end wrench, the force of your hand pushing down some distance away from the bolt head causes the thing to turn. Or if you're changing a tire, if you got just a little old straight socket wrench and tried to turn those lug nuts, it wouldn't work very well. So you get one of these lug wrenches where you can apply your force out some distance away from that pivoting axis, and now it's easier to turn. If you have a crowbar and you're trying to lift a heavy box, let's say, you can stick the crowbar under there and go out to the end of the handle, and even though you may not be very strong, your force times that distance will wind up lifting that weight. It's the same principle that causes a claw hammer to work. So moment is force times distance. The magnitude of that moment depends on how big is the force and how long is the distance. Here's an example. If you want to get a hole punch, if you get a economy model of hole punch, like the one at the bottom here, you can punch holes in a few sheets of paper, but if you want a heavy-duty puncher, you go get one of these jobs, and they have a long handle that sticks out from the pivot point. So you take your same hand that you used before, but you push some distance away from that axle, and now you can apply greater moment and you can punch more pieces of paper. Or let's say you work for the city and you want to lift one of these heavy cast iron sewer access covers. They're very heavy, and so you could try to lift it, but it would be hard. But look at this ingenious device. This device, there are several pictures here, it has a long lever arm, a long moment arm, out away from the pivot point, and so you attach the hook to the cover, and then you go out a distance and apply a force, and you generate a big moment, the tendency of a force to cause rotation. If you're lifting, let's say, a brick or a piece of concrete, if you hold the brick close to your shoulder, feels okay, you can lift it. If you stretch your arm out and hold that heavy weight out away from your shoulder, it's still the same weight, but because you've increased the distance, it now has a much greater tendency to cause rotation. In other words, this brick is harder to hold up when you stretch your arm out because you have a bigger moment. Notice that the distance is perpendicular to the force, and we're going to talk about this in more detail next time. So from the pivot point, perpendicular to the line of action, that's the distance. You may have seen a thing called a torque wrench, and a torque wrench is measured in foot-pounds if you're in the imperial system, the US system, or in Newton meters if you're in the metric system, or it might be in the imperial system. It could be foot-pounds or inch-pounds. I will just point out that technically speaking, we should be calling it pound-feet because moment is force times distance. But everybody says foot-pounds and inch-pounds and Newton meters, so that's what we're sticking with. Now, you know how a force has a magnitude and a direction? A moment has a magnitude and a direction also. And because moment is rotation, the direction is, what direction does it rotate, clockwise or counterclockwise? And it turns out that we have all agreed that if a thing rotates clockwise, we're going to call that negative moment. And if a thing rotates counterclockwise, we're going to call that positive moment. And that's the same system that we use in AutoCAD. You know, when you rotate a line, if you rotate it from the 0 line up towards the 90-degree line, that's counterclockwise, and AutoCAD thinks of that as positive degrees. This is also known as the right-hand rule, and to help yourself remember which direction is positive or negative moment, think of the right-hand rule. So take your right hand and look at your thumb. You'll see your fingers curling. Your fingers are curling in the positive direction. They happen to be curling counterclockwise. That's positive moment. So we can use moment in all kinds of ways to figure out how things are balancing and how much weight. So here's two people. Each one weighs 100 pounds and is 10 feet from the pivot point. So force times distance. This person has a positive 1,000 foot-pounds. This person has a negative 1,000 foot-pounds. Now, could we figure out, if we put a bigger person on the teeter-totter, how far away from the pivot point would they have to be in order to have this teeter-totter balance? So if the person on the right causes a negative moment of 1,000 foot-pounds, you need a positive 1,000 foot-pounds on the left in order to balance. So if this person weighs 200 pounds, how many feet do we need to make 1,000 foot-pounds? Looks like we need 5 feet. And I'm going kind of fast here. I want to zip through this so we can look at our homework, but we will come back to some of these moment calculation problems over time. I would like now to look at this quiz problem, and this problem, this is out of our book, and he's saying we've got a box that weighs 25 pounds, and we could draw an arrow right through the middle of the box to represent that 25-pound weight if we wanted to. It's an 8-foot box, so it's 4 feet from the middle of the box to the pivot point. And then we have somebody pulling with let's say a rope, pulling with 20 pounds of pull on the top corner. And that's going to cause that box to try to tip over. The question that he wants you to answer, actually there are two questions. One, what is the total moment around point A? So we've got the overturning moment caused by the pull and the resisting moment caused by the weight. What do those add up to? And then, once you know that, does the box tip over? So let's now go look at this CAD drawing. I have inserted our image here, and I redrew it in CAD. So here's the 25-pound weight, the arrow going through the middle, and here's the 20-pound pull at the top corner. And if we want to figure out moment equals force times distance, we're going to have to figure out, okay, which distance goes with which force. So let's look first at the rope that's pulling on the top corner. And let's figure out, is that the 5-foot distance or is that the 4-foot distance? Well, if you do an old rotate here around that point A, so if you, oops, I've got my ortho turned on. If you rotate that arrow, you'll notice from the pivot point perpendicular to the line of action, looks like it's that 5-foot height that is the distance. Okay, so we could go moment equals force times distance. We could go moment equals 20 pounds times a 5-foot distance. Looks like this overturning moment must be 100 foot-pounds. Let's now look at the resisting moment from the weight of the box. And here it is. And let's see what the arrow from the weight of the box tries to do with respect to that pivot point. And I've drawn the arrow a second time over here just so we can rotate it. So I'll use that that thing that I drew there as point A. That's supposed to be our pivot point. And now we can rotate that resisting moment. See how it's turning around point A? So it looks like that 4-foot distance from the 25-pound arrow to the pivot point, that's our distance. So it looks like this moment would be 25 pounds times 4 foot. That's 100 foot-pounds. What happens when we have negative 100 foot-pounds plus positive 100 foot-pounds? What do those add up to? You might be thinking, those sounds like those add up to 0, and you would be right. If the total moment adds up to 0, and if moment is the tendency of a force to cause rotation, if you have 0 moment, do you have a box tipping over? No, you do not. The moment adds up to 0, we don't have any tipping over happening. Now that's at this moment in time. If we added just a tiny bit more force to that rope pulling on the top, it would tip over, because now we would have more overturning moment than we have resisting moment. But at this snapshot in time, that thing is in equilibrium. It is just sitting there. It is not turning.